The Sleepy Physicist exists because people choose to keep it alive. If you want it to stay, Patreon link is in the description.
Something is gone, not moved, not changed, not hiding somewhere smaller than you can see, gone. And the place where it was, the exact coordinates in space and time where it existed one moment before, holds no mark of it. No dent, no warmth, nothing that says something was here. That is the thing I keep coming back to, that specific wrongness. Before we get anywhere near an explanation, I want to sit with that for a moment. Because your instincts about the physical world, and they are good instincts, honestly, built over a lifetime of touching things and watching things move and seeing nothing ever truly disappear, those instincts are going to push back against what this video is about. And I think they should. I think that resistance is worth feeling before we start dissolving it. There is something I want to share. I make this in the late hours. When everything else in the day is done, I sit down and I work on this, because I believe it is worth working on. For a long time, the future of this channel was uncertain, and I carried that quietly while making the videos. What has started to change that is the people who have joined on Patreon. Each one of them shifted the odds a little further in the right direction. Joining is not just support, it is a signal that this should exist. We are still working toward 200 members, but the math is starting to look different. If you want to be part of changing it, the link is in the description. Now let's get back to our topic. You have spent your entire life in a world that conserves things. A candle burns and the wax becomes heat and gas, and a faint smell of smoke, it doesn't become nothing. A building comes down and the rubble sits in the street. Water evaporates and somewhere eventually it rains. Things change their form constantly, aggressively, sometimes violently, but they do not vanish. So when a physicist tells you that a particle, a real physical thing with a mass and a charge and a spin, a thing that interacts with other real things or can simply stop existing, it is reasonable to feel that this is wrong. Not unfamiliar. Wrong. The way it is wrong when a sentence ends before it. It does not feel like physics. It feels like a magic trick you haven't been shown the mechanism for yet. But here is the part that doesn't resolve neatly. It isn't a trick. The particle in question, the one we're going to follow through this video, is an electron. Specifically one electron. Somewhere at some particular moment it encounters something it cannot survive, its own opposite number. A positron, same mass, reverse charge, every additive property flipped like a mirror held up to the original. They meet, and what happens next is not a collision in any sense your body understands. They do not bounce, they do not break apart, they do not scatter. They become something else entirely. Two photons moving in opposite directions, light more or less, and the electron, the thing that was there, is not there anymore. This is where it starts. This question, which is going to get considerably stranger before it gets anything resembling settled. Where did it go? Not the energy. We can account for the energy. Not the momentum. That's fine. Conserve, carried away cleanly by the photons. What I mean is, the electron had a specific quantum state, a spin, a set of properties as precise and individual as anything in the physical world can be. It had a kind of, I'm not sure identity is the right word, but nothing better is arriving right now, a kind of informational fingerprint. Every measurable thing about it stacked up, and then the electron was gone. So where is the fingerprint? This is the question physics has been sitting with, in one form or another for decades. Not just for electrons meeting positrons in a controlled annihilation, but for everything, for matter falling into black holes, for the long, slow evaporation of the most extreme objects the universe produces. The question underneath all of it is the same uncomfortable one. Does the universe keep records? Is there some ledger, somewhere in the structure of reality, where every state that ever existed is still written down in some form? Or is deletion possible? Is there a mechanism, natural, lawful, not magic, by which something can happen to a physical system such that the past is genuinely irrecoverably gone? Most of physics says no, says it loudly, and with considerable mathematical backing. But the universe has a tendency to make things complicated in exactly the places where the answer seems clearest. The electron is gone. The photons are moving apart. The room, and there is a room somewhere with equipment that registered this, with a particular hum from a cooling system and the smell of something faintly electrical, the room is unchanged. But the question is still in it. That is where we are starting. Right here in the space where something used to be. Before the question of where something goes, there is a quieter question sitting underneath it, one that tends to get skipped in the rush toward the interesting part. What was it exactly that was there? Picture the space around you right now, not the walls, not the objects, not even the air, but the space itself, the invisible medium that everything you can see is suspended inside. Physics says that space is not empty. It has never been empty. Running through it in every direction, at every scale, through the floor and the ceiling and the particular darkness outside your window and the gap between your fingers, there are fields. Not force fields in any dramatic sense, just fields. Mathematical quantities that take a value at every point in space and every moment in time, continuous and vast and, frankly, a little difficult to hold in your head without it sliding away. There is an electron field. It covers everything. It has always covered everything, or at least everything we have access to. It does not pulse or glow or announce itself. It simply exists draped across the universe like something that has been there so long it no longer has a shape you can point to. An electron, the thing you were probably picturing when the last chapter said the word, is what happens when that field gets disturbed. A localized excitation which sounds technical and is, but the idea underneath it is almost ordinary. The field gets nudged somewhere in some small region of space. And that nudge behaves like a particle. It has mass. It has charge. It has spin. It moves. It interacts with other nudges in other fields. From the outside, from any practical measurement you could make, it looks exactly like a discrete object. But it is not a discrete object. It is, and this is the part I keep finding genuinely strange no matter how many times I turn it over, it is a condition of the field. A state the field is in, locally, temporarily. The electron is not a thing sitting in the field the way a stone sits in water. It is more like, well, I was going to say it is like a ripple, but that is almost too clean, too visual, and the reality is messier than a ripple. It is more like a specific kind of tautness in the field, a region of heightened something, and that tautness propagates through space and interacts with other tautnesses in other fields. And we call the whole arrangement a particle because the word is useful and because nothing better has won the argument yet. This matters. It matters specifically for what we are asking in this video. Because if an electron is an excitation of the electron field, then when an electron vanishes, when it annihilates, when the localized disturbance that we were tracking stops being traceable, the field does not vanish with it. The field is still there, still covering everything, still threading through the space where the electron was, and the space an enormous distance from it, and the space that has never had a particle anywhere near it. The field is unchanged in the sense that fields are unchanged, present, continuous, humming along at its background level. What ended was the excitation. The ripple, or whatever we decide to call it, stopped being a ripple. The field returned locally to a quieter state. And the question of where the electron went is, at this level of description, a question about what happened to the information that was encoded in that excitation, the shape of it, the spin, the specific quantum numbers that made this particular disturbance what it was and not something else. Because the field doesn't care. The field is not storing that information in any obvious way, not keeping a record of which excitations it has hosted, not maintaining a kind of memory of the ripples that have passed through it. Or, and this is the part where I find myself growing less certain, not more. Perhaps it does, in some way that is not obvious at all, in the correlations that remain between field states even after the particle that produced them is gone. Quantum field theory does something quietly radical when you look at it from this angle. It does not just reframe what a particle is, It reframes what it means for something to be gone. The particle was never a self-contained object with an independent existence. It was always a relationship between a field and a region of space. When that relationship ends, the field persists, the region persists. What persists of the relationship is the question that is going to stay with us for a while. The word gets used loosely. Information. It gets used to mean data, knowledge, content, meaning, memory. It gets attached to computers and libraries and the human brain and the way a face can carry an entire history in the arrangement of its features. The word has accumulated so many uses that it has started to feel like it means something slightly different every time it appears. Physics uses it differently from all of them. When a physicist says information, they mean something specific and almost brutally concrete. They mean the complete specification of a physical state, not a summary, not a useful approximation. Every position, every momentum, every spin, every charge, every quantum number of every particle in a system, recorded with the precision that quantum mechanics allows at every moment in time. The total description. Nothing selected, nothing rounded, nothing left out because it seemed unimportant. That is what information is in this context. It is worth pausing on how much that actually means. Take a single hydrogen atom. To specify its state fully, you need to know the quantum state of its electron, the energy level it occupies, its angular momentum, its spin orientation. You need the same for the proton. You need the correlations between them. You need, in principle, the entanglement between this atom and everything it has ever interacted with, which spreads outward in a network of dependencies that gets very large very fast. A single hydrogen atom fully specified is already a complicated object. A gram of hydrogen contains roughly 600 billion trillion of them, and yet that is still just hydrogen. Just one element, just a gram. The full informational content of any macroscopic object is staggering in a way that the word staggering does not really reach. It is the kind of number that stops being a number and starts being a texture, a sense of depth that doesn't resolve no matter how long you look at it. But the size of it is not the point. The point is what the information does. In classical physics, if you knew the complete state of every particle in a system at one moment, you could, in principle, with sufficient computation, calculate the state at any later moment and run it backward. The past and future are both recoverable from the present. Information is the thing that makes that true. It is not a record kept somewhere external to the system. It is the system. The physical state and the information content of that state are not two separate things. They are the same thing described from two directions. Quantum mechanics complicates this, as quantum mechanics complicates most things. The uncertainty principle means you cannot simultaneously know position and momentum to arbitrary precision. The act of measuring certain properties disturbs others. The state of a system before measurement is genuinely different from the state after. These are real constraints, not limitations of instruments or technique, and they mean that information at the quantum level behaves in ways that classical intuition handles poorly. But, and this is the part that matters for what we're doing here, quantum mechanics does not say that information disappears. It says information transforms, it says information spreads, becomes entangled with other systems, gets distributed across degrees of freedom that are increasingly difficult to access. Scrambled, in the technical sense, present but practically unreachable, the way something dropped into a deep, turbulent body of water is still there even after the surface has closed over it. The state changes. The information does not leave. This is not a convenient assumption physicists make to keep their equations clean. It is a consequence of the mathematical structure of quantum mechanics itself. The Schrödinger equation, which governs how quantum states evolve in time, is deterministic and reversible. Feed it a state at one moment, and it tells you the state at any other moment, forward or backward. That reversibility is only possible if nothing is lost. If the evolution destroys information genuinely, irrecoverably, the equation breaks. Not in a subtle way, in a fundamental structural way. Information is the thing that makes physical law reversible. Without it, the past cannot be recovered from the present. Without it, physics becomes a one-way door. I find this, and I am aware this is a slightly strange thing to find, and I find this almost morally weighted. The idea that the physical world is built such that nothing is ever truly erased, that every state that has ever existed leaves something behind in the structure of what follows, not a memory in any human sense, not a ghost, just a constraint. A before that is recoverable in principle from the after. Whether that principle holds in every situation, whether there are places in the universe where information is not just scrambled but genuinely gone, is exactly what the rest of this video is going to press on. The word for now means everything, the complete account, the total specification. What happens to it is the question. There is a kind of law in physics that doesn't feel like a law at first. It doesn't arrive with a name you immediately recognize. It doesn't describe a force or a particle or a measurable quantity you can hold an instrument up to. It describes something more like a rule about how rules work, a constraint on the shape that physical evolution is allowed to take. Unitarity is that kind of law. The word comes from mathematics. A unitary transformation is one that preserves certain lengths, certain inner products, certain geometric relationships between vectors in an abstract space. That is the technical definition, and it is not especially illuminating on its own. What it means physically is something you can approach from a few directions, and none of them are wrong exactly, but some of them carry more weight than others. The lightest version, probabilities always sum to 1. If a quantum system can be in any of several states, and you ask for the probability of each, those probabilities must add up to exactly 1, not approximately, not on average, exactly. This sounds obvious until you start thinking about what it would mean if it weren't true. If probabilities sum to something less than 1, there would be outcomes with no explanation. Situations the universe could reach by following its own rules that have no accounting in any subsequent state. Something would have happened and the physics would not know it happened. That is not a small problem. That is physics losing its grip on itself. The heavier version, quantum evolution, is reversible. Not reversible in the practical sense of being able to run things backward with enough effort, but reversible in the structural sense that a complete description of the present state of a system contains, without loss, a complete description of every past state. The mathematics that takes a quantum state from one moment to the next can always be inverted. The future can be calculated from the present, and, crucially, so can the past. If you know where a system is now in the full quantum sense, you know where it was. Not probably. Exactly. This is the thing unitarity actually demands. Not just that probability is conserved, but that time works in both directions with equal completeness. That the arrow you follow into the future leaves an unbroken trail back. And this is where it starts to feel heavy, if you let it. Because the implication of that reversibility, the thing sitting quietly inside it, is that information cannot be destroyed. Cannot be, not by any physical process that obeys the rules. Because if information were destroyed, the trail would break. There would be a moment in the history of the system from which the past could no longer be recovered. 2 different histories could arrive at the same present state. And if 2 different pasts can produce identical present states, then the mathematics cannot be inverted. The evolution is no longer reversible. Unitarity is violated. It all connects. The reversibility, the probability conservation, the impossibility of information loss. They are not thus 3 separate requirements. They are the same requirement described from 3 angles. Violate one and you have violated all of them, whether or not the violation looks dramatic from the outside. Susskind, Banks and Peskin worked through what such a violation would actually cost. It is not, and this is worth saying carefully, It is not merely an aesthetic problem, not a matter of the equations looking untidy. A small violation of unitarity, they showed, would either produce interactions between distant regions of space-time that shouldn't be able to communicate, which is a causality problem of the most serious kind, or it would produce violations of energy momentum conservation large enough to be catastrophically inconsistent with everything else we know. A little bit of unitarity violation is not a small error you can quarantine. It spreads. It pulls other things down with it. A tiny leak in this particular law is not a tiny problem. This is why physicists treat unitarity the way they do. Not with reverence exactly, physicists are not especially prone to reverence, but with a particular wariness about what it would mean to abandon it. It is load-bearing. It is the kind of assumption the rest of the structure sits on without most people noticing until someone asks what would happen if you took it away, and the answer turns out to be most of the structure. The image that comes to mind, and I held off on this for a while because I wasn't sure it earned its place, is a film that can be run in either direction. Not because someone chose to run it backward, but because the film itself contains no information about which direction is forward. Every frame carries the entire adjacent frame inside it. Cut the film anywhere, and the pieces on either side still hold the complete record of everything that came before and after. Unitarity says reality is that film. Every moment is a complete record. Every state is reversible. Nothing is cut. What happens then when a particle vanishes and the moment seems to offer less than a complete record? That is the part of the film we need to look at more carefully. The electron has been travelling, not in a straight line, not with any particular destination. Particles at this scale do not have destinations. They have probability distributions that collapse into positions when something forces the question. But for our purposes, for the purpose of following this one electron through the question we are asking, it has been moving through a region of space, carrying everything it is, a mass of just over 910 thousandths of a trillionth of a gram, a charge of -1 in the units we use, a spin of 1/2, a quantum state that is, in its complete form, a more detailed document than it looks. It carries what it is, all of it, all the time. The positron has been doing the same thing. Somewhere in the same region of space it has been moving, carrying its own account. Same mass, same spin, but charge reversed, and every other additive quantum number reversed with it. Not the electron's twin, more like it's the word that keeps almost arriving is negative, but that is too flat for what it actually means. The positron is the electron turned inside out in every measurable way that can be turned. Where one is positive, the other is negative. Where one carries a particular kind of weak force charge, the other carries the opposite. They are, in this very specific technical sense, genuinely each other's inverse. And they are slowing. Particles at high energy move past each other with barely an acknowledgement. The interaction cross-section, the effective target each one presents to the other, shrinks as speed increases, but these two are losing energy to their environment, thermalizing, which is a clinical word for something that feels almost like fatigue. They are becoming slower, cooler, more vulnerable to each other's presence. The electromagnetic pull between them is now strong enough to matter. Opposite charges attract. This is the oldest rule in the book, and it does not care about the strangeness of what is being attracted. The electron and positron begin to orbit each other. What forms is called positronium. It lasts somewhere between 100 and 1/10 of a nanosecond, depending on the spin configuration. Parapositronium, where the spins are anti-parallel, goes quickly. Orthopositronium, with parallel spins, lingers a little. Neither lingers long. But while it exists, positronium is a genuine bound state, a system. Two particles held together by the same force that holds electrons to protons in ordinary atoms, executing a shared orbit around a common centre of mass. The orbit is strange, though. In hydrogen, the electron's mass is negligible compared to the proton's, so the proton barely moves while the electron does most of the circling. In positronium, the masses are identical. Both particles orbit the midpoint between them. Neither is the center. Neither is the one being held. That detail keeps striking me as significant, even though I am not entirely sure what to do with it. Both particles carrying everything they are, both in motion, both, in some sense, equally the subject of what is about to happen. There is no heavier one standing still while the lighter one spirals in. They are falling toward each other at exactly the same rate, which means the center of this small temporary system is a point in empty space that neither of them occupies. The ghost atom, that is the phrase that surfaces, and I am going to leave it even though it is slightly too neat. Positronium is real, measurable, detectable, with a real spectral signature and a real set of energy levels, but it has this quality of existing between categories. It is matter. It is also, in some fundamental sense, matter already in the process of becoming something else. The structure is there, the binding is real, but the endpoint is written into the configuration. Parapositronium decays in roughly 125 picoseconds. That is 125 trillionths of a second, which is a span of time your nervous system cannot register, which is shorter than the time it takes light to cross a room, which is, by the standards of particle physics, not even especially brief. There are particles that last far less, but it is long enough for the two particles to have been, briefly, a thing together, long enough for the orbit to have been real, long enough to carry everything they are into the moment of ending. It takes no time at all. That is not quite accurate. Nothing in physics takes genuinely zero time. But the annihilation event itself occurs on a timescale so compressed that describing it as brief feels like an understatement so severe it almost becomes a different kind of wrong. The interaction happens. The particles are there, then they are not. What sits between those two states is not a process you can slow down and examine, not a sequence of sub-steps with intermediate configurations you could photograph if your camera were fast enough. There is a before, there is an after. The during is not really a place you can stand. What the before contains, two particles, orbiting a shared center, each carrying mass, each carrying charge, each carrying a precise quantum state that specifies everything about them that physics considers real. The electron with its negative charge and its spin and its particular half-integer angular momentum. The positron with all of that reversed. Together, in the positronium configuration, they form a system whose total charge is exactly zero, whose total lepton number is exactly zero, whose total of every additive quantum number is, by the arithmetic of opposites, exactly zero. This is not incidental. It matters enormously for what comes next, because what comes next has to balance against that zero. Whatever emerges from this event carries the sum of everything the system contained, and the sum is zero charge, zero lepton number, zero baryon number. The photons that emerge, two of them in the parapositronium case, are electrically neutral, carry no lepton number, carry no baryon number. They are, in that sense, the only things that could have emerged. The conservation laws do not allow most alternatives. They narrow the space of possible outcomes down to something very small. And then quantum electrodynamics, the theory that governs how light and matter interact, selects from within that space. Two photons, moving in opposite directions, each carrying 0.511 mega electron volts of energy. That number, 0.511 mega electron volts, is the rest mass energy of a single electron, or a single positron. Both particles had it. Together they had 1.022 mega electron volts of rest mass energy, plus whatever small kinetic energy they carried in their slow orbit. That energy does not disappear. It cannot. Energy conservation is, if anything, even less negotiable than the other conservation laws, and it says that the total energy of the system before the event must equal the total energy after. The photons carry it. Exactly. Down to the last fraction. Momentum is conserved too. The two photons travel in opposite directions because they must, The system's total momentum before annihilation was approximately 0, and so the momenta of the two photons must cancel each other, which requires them to travel in exactly opposite directions with exactly equal magnitudes. Back to back. Perfectly anti-parallel, not as a preference but as a requirement. Angular momentum is conserved. The spin configuration of the positronium state determines how many photons are produced and what polarization relationships they carry. Parapositronium, with its anti-parallel spins and total spin 0, produces two photons whose polarizations are perpendicular to each other. This too is not a choice. It follows from the numbers. So everything is conserved. Energy, yes. Momentum, yes. Angular momentum, yes. Charge, lepton number, every additive quantum number, all of them 0 before, all of them 0 after. The ledger in these terms is clean, and yet the electron is gone, the positron is gone, not transformed into the photons the way water transforms into steam, carrying its molecular identity through a change of state. Gone in a harder sense. There is no electron hiding inside the photons. There is no positron distributed across their electromagnetic fields. The particles that existed before this event do not exist after it, and the things that exist after it are not the same things in a different form. They are different things. This is the part I find fussy, maybe, is the word. This is the part where the accounting feels almost too clean to trust. The numbers all balance. Every conserved quantity is accounted for. The physics is satisfied, technically, completely. And still there is this residue of a question that the conservation laws do not touch. What happened to the specific quantum state of the electron? Its spin, its particular orientation, the complete informational fingerprint that made it this electron, and not some other configuration of the electron field. The conservation laws track totals. They do not track identity. The photons carry energy. They carry momentum. They carry polarization, which encodes something about the spin state of the system that produced them. They carry in their entanglement with each other a relationship that reflects the quantum state of the positronium they came from. Whether that is enough, whether the photons carry the complete informational content of the particles that became them, or only a partial accounting, is the question the next part of this video is going to press on. The two photons are already moving apart at the speed of light. The place where the electron and positron were is empty. What the emptiness contains is the part we have not yet looked at. The two photons are moving apart. By the time you finish reading that sentence, they have travelled a distance your body cannot meaningfully picture, not because the distance is abstract, but because the speed is real, and the scale of it does not fit inside ordinary intuition. They are moving at the maximum speed the universe allows in exactly opposite directions, and the space between them is growing at twice that rate. And yet they are not independent. This is the thing that takes a moment to settle, and I want to give it that moment rather than rush past it toward the explanation. The two photons that emerge from the annihilation are entangled, not connected by a wire or a signal or any physical link you could trace between them. Entangled in the quantum mechanical sense, which means that the description of one of them is not complete without reference to the other. They are, in some precise mathematical sense, a single system that happens to be distributed across two locations that they're getting farther apart every instant. What does that mean for what they carry? Start with polarization. Each photon has a polarization, an orientation of its oscillating electromagnetic field, a direction the field points as the photon moves. Polarization is a real measurable property. You can put a polarizing filter in the path of a photon and determine with some probability which way it is polarized. In ordinary light, photons have polarizations that are independent of each other. One photon's polarization tells you nothing about another's. In the photons produced by parapositronium annihilation, this is not true. The spin state of the positronium system before annihilation was 0. The electron and positron had anti-parallel spins, combining to a total angular momentum of 0. Angular momentum is conserved through the annihilation. So the two photons must together carry zero total angular momentum. And the constraint that this places on their polarizations is exact. They must be perpendicular to each other. If you measure one photon's polarization and find it oriented vertically, the other photon's polarization is horizontal. Not probably, not on average, every time. But, and this is the part where it gets interesting, where it gets genuinely strange in the way physics occasionally earns, neither photon has a definite polarization before you measure it. Not because the polarization is hidden and you simply don't know it, because it isn't there yet, in the sense of being a determinate fact about the universe. The photon exists in a superposition of polarization states until a measurement forces it to commit to one. And the instant it commits, the distant photon commits to the perpendicular orientation, regardless of how far away it is. John Wheeler noticed this first in the 1940s, before the word entanglement had become common currency in physics. He was working through the quantum mechanics of positronium decay and recognized that the correlation between the output photons was not a classical correlation, not the kind you get when two gloves from the same pair are separated and you find one in your left hand and know immediately the other is right-handed. It was something more stubborn than that, more tightly coupled. The glove analogy is comfortable, but no, I keep reaching for it and it keeps being not quite right. The gloves were always one or the other. The photons were not. The photons carry this entanglement the way they carry energy and momentum, completely, continuously, all the way to whatever detector eventually receives them. The entanglement does not decay with distance. It does not weaken as they move apart. It is a property of the joint system, not of either photon individually, and the joint system persists even as its components separate across space. Now, what does this mean for information? It means that the quantum state of the positronium system, the complete specification of the electron-positron pair just before annihilation, is not lost in the annihilation. It is encoded in the joint quantum state of the two photons. The correlations between them carry the angular momentum information. The entanglement structure carries the spin state. The energies and momenta carry the mass and velocity information. You could, in principle, this is demanding in practice, requiring measurements that are extraordinarily difficult to perform, reconstruct the quantum state of the original pair by measuring both photons with sufficient completeness, the information transferred. That is the pivot this chapter exists to reach, and I want to be careful about what it means and what it doesn't. It does not mean the electron survived in some hidden form inside the photons. The electron is gone. The positron is gone. The particles do not persist. What persists is the informational structure that specified their state, carried forward in the correlations between two particles that did not exist before the annihilation, encoded in a joint quantum state that is, mathematically, the successor to the state that preceded it. The universe kept the record, not by keeping the electron, by transferring what the electron was into a new physical system that could carry it forward. I think this is the thing the whole video has been building toward, or at least the first version of it. The answer to the opening question, the one about whether anything goes with the particle when it vanishes. Something goes with it. Everything goes with it. The specific something is the quantum state, the informational fingerprint, and it does not stay behind in the empty space where the particles were. It leaves with the photons. It leaves encoded in their relationship to each other, in the entanglement that ties them together, across whatever distance they eventually reach. The photons remember, not in the way a brain remembers, not as a narrative or an image, in the way physics means when it says a system retains information. The state is there, recoverable in principle, present in the correlations if you know how to read them. The electron vanished. The record of the electron did not. And yet this is the simple case, the clean case where the photons escape and the information travels freely into open space. The question we have not yet asked is what happens when that is not possible? When the annihilation happens somewhere the photons cannot leave, when the information has nowhere to go that we can reach. That case is considerably harder. Take everything we have just established and move it, not the physics, and the physics stays exactly as it is. The electron still meets the positron, the annihilation still happens, the two photons still emerge carrying the entangled record of everything the particles were. All of that remains true. What changes is the location. What changes is the environment the event happens inside. Move it to the interior of a black hole. The photons are produced. They move outward from the annihilation site as photons do, at the speed of light, carrying their entanglement, carrying the complete quantum state of the original pair in the correlations between them. They move toward the edge of the region they are inside, which is the event horizon, which is the boundary beyond which the geometry of space-time does something that has no everyday equivalent and is genuinely difficult to describe without making it sound more dramatic than it is. The photons do not cross it, not because something stops them, not because there is a wall or a barrier or any physical structure at the horizon that a passing photon would encounter. The horizon is not a place in that sense. It is a condition, a surface defined by the geometry of the space-time around a sufficiently massive object, a surface at which the escape velocity equals the speed of light, which means that any object moving at or below the speed of light, which is all objects, cannot move away from the center fast enough to actually move away from the center. The photons travel at the speed of light. At the horizon, moving at the speed of light in the outward direction is exactly equivalent to standing still. Past it, outward is no longer a direction that leads out. The information encoded in those photons goes nowhere we can reach. Now, a black hole is not, in common usage, presented as the universe's most extreme test of a principle about information. It is presented as extreme in other ways: extreme gravity, extreme density, extreme curvature, the kind of object that ends stars and bends light and sits at the center of galaxies with a patience that is almost structural. These things are true and they are genuinely extreme, but the extremity that matters for what we are doing right now is quieter than any of them. A black hole is a place from which information cannot escape. That single fact, which sounds like a technical detail about photon trajectories and escape velocities, turns out to be one of the most destabilizing ideas in modern physics. Because if information cannot escape, and if the black hole eventually ceases to exist, which, as we will see, it eventually does slowly, over an almost incomprehensible span of time, then the information that fell in has nowhere to emerge from. It went in, the container dissolved, and the question of where it went becomes genuinely structurally difficult in a way that the annihilation question, as we posed it in the previous chapters, was not. In the open space annihilation, the photons escaped. The information left the scene in a form that could, in principle, be recovered. The universe was, in that sense, cooperative. The information travelled. The ledger remained intact even as the format changed. A black hole refuses this cooperation. The ledger goes in, the ledger does not come out, at least not in any obvious form. And the black hole, this is the part that took decades to establish and is still not entirely settled. The black hole does not simply sit there holding the information indefinitely. It changes, it loses mass. Slowly, absurdly slowly by most standards, but continuously and without reversal, it radiates, and the radiation, as far as anyone could initially determine, carries none of the information stored inside. This is not a story about a dramatic catastrophe. It is a story about a slow leak and an accounting problem. Matter falls in, carrying information. Radiation comes out, apparently carrying none. The black hole shrinks. Eventually, after a period of time so long that the current age of the universe is a brief prologue to it, the black hole is gone, and the question sitting in the space where it was is the same question we started with, but harder and with considerably more on the line. Where did the information go? In the annihilation case, we found it in the photons. The photons remembered. The entanglement preserved the quantum state of the original particles and carried it forward into a form that, while demanding to work with, was in principle recoverable. The information did not die, it transferred. But what transfers when nothing can leave? What carries the record when the carrier cannot escape? These are not rhetorical questions in the sense of having obvious answers that the chapter is withholding for effect. They are open questions in the literal sense, Questions that some of the most technically sophisticated physicists the last 50 years have spent careers on. Questions that have produced fierce disagreements and surprising resolutions, and, frustratingly, new paradoxes at every level of apparent resolution. The black hole is where our annihilation question goes when it gets serious. When the easy version, the version where the photons escape and the information travels freely, is replaced by the version where nothing escapes and the universe is asked to account for what it cannot show us. The accounting, it turns out, involves ideas that would have seemed irrelevant to the question when it was first posed. Ideas about surfaces and about dimensions, and about whether the interior of a region and the boundary of that region are, in some deep sense, the same description written in different languages. Those ideas are coming. But first, the problem needs to become properly clear. In 1974, Stephen Hawking did something that surprised nearly everyone, including, reportedly, himself. He proved that black holes are not black. The calculation was not simple. It required holding quantum field theory and general relativity in the same framework simultaneously, which is a technically demanding thing to do, and which physicists are, in most contexts, careful to avoid because the two theories do not fit together cleanly. Hawking pressed through that discomfort and found something sitting at the boundary between them. Something that classical physics, which treats the event horizon as a geometrically clean surface with no particular physical behaviour, had missed entirely. At the horizon, the quantum vacuum does something. The vacuum of quantum field theory is not empty in the way the word vacuum implies. It is a frothing, restless thing. Virtual particle pairs constantly flickering into existence and annihilating each other before they can be directly detected. A permanent low-level turbulence in every field that permeates space. Ordinarily, these virtual pairs appear and disappear too quickly to have macroscopic consequences. But at the event horizon of a black hole, the geometry of spacetime is doing something so extreme that it interferes with this process in a specific and consequential way. Pairs of virtual particles form near the horizon. One member of the pair falls inward, past the horizon, into the black hole's interior. The other member, deprived of its partner and unable to annihilate, becomes real. It escapes outward. From a distance, from the perspective of someone watching the black hole from far away, this looks exactly like the black hole is radiating, emitting a steady stream of particles from its vicinity, losing energy, losing mass, slowly and continuously shrinking. This is Hawking radiation. The temperature of this radiation is extraordinarily low for any black hole that could plausibly exist in the current universe. A black hole with the mass of the Sun would radiate at roughly 60 nanokelvins, a temperature so close to absolute zero that it is unmeasurable against the cosmic microwave background, which is itself already cold enough to be difficult to work with. The radiation is real in the mathematical sense, clearly and rigorously predicted, but observationally invisible for any black hole we are likely to encounter. None of that is the devastating part. The devastating part is what kind of radiation it is. Thermal radiation is radiation in equilibrium with a temperature. A hot object glows, and the spectrum of that glow, the distribution of energies across the photons it emits, is determined entirely by its temperature. Not by what the object is made of, not by its history, not by what it is absorbed or processed or contained. A lump of iron glowing at a given temperature and a cloud of hydrogen gas glowing at the same temperature produce indistinguishable thermal radiation. The spectrum is universal. The temperature is the only parameter. Hawking showed that the radiation emitted by a black hole is thermal in exactly this sense. Its spectrum is determined by the black hole's temperature, which is determined by its mass. That is all. The radiation carries no record of the star that collapsed to form the black hole, no record of the books and chairs and people and fields of grass that subsequently fell in, no record of the electron-positron annihilation we have been following through this video. The radiation is, in the precise technical meaning of the word, featureless, a perfectly random sample drawn from a thermal distribution, maximum entropy, the kind of output you get from a system that is forgotten, and I am using that word loosely, almost uncomfortably, everything about its input. Static, not silence. Static. Silence would be informative. Silence would tell you the system produced nothing, which is a fact. Static tells you nothing about the system at all, which is a different and worse condition. The radiation that escapes the black hole, Hawking's calculation said, is static. The black hole is broadcasting continuously and saying nothing. Now extend this forward in time. The black hole is radiating. It is losing mass. Every particle that escapes carries away a tiny fraction of the black hole's energy. And the mass decreases, and as the mass decreases, the temperature increases. Smaller black holes are hotter, which is counterintuitive and correct, and the radiation intensifies and the mass falls faster. And eventually, after a period of time that makes the current age of the universe look like a casual Tuesday afternoon, the black hole evaporates completely. It is gone. And everything that fell in, every quantum state, every electron spin, every complete informational specification of every particle that ever crossed the horizon has been replaced by the thermal radiation that encodes none of it. The before and the after do not connect. The state of the radiation does not determine the state of what fell in. You cannot run the evolution backward. The trail, which unitarity demands must be unbroken, appears to be broken. The film, to use the image from the earlier chapter, has been cut. Not a frame missing here or there, an entire sequence replaced with noise. This is why the prediction was terrible. Not because Hawking was wrong about the radiation. The calculation is, as far as anyone can determine, correct in its essential features, a genuine result about quantum fields in curved spacetime. But because the radiation, being thermal, being featureless, being maximally entropic, implies something that should be impossible. It implies that the universe forgot. Hawking believed it. For a long time he believed it rather firmly, which put him in direct conflict with quantum mechanics, which says, categorically, structurally, as a consequence of its mathematical foundations, that the universe does not forget. One of them had to be wrong. Which one and why and what the resolution cost? That argument consumed decades. Let's be specific about what breaks, not vague. Not the foundations of physics are threatened, in the way that phrase gets used when something surprising turns up and someone wants it to sound important. Specifically, concretely, in the way an engineer would want to know, if information is genuinely destroyed in black hole evaporation, what exactly stops working? Start with unitarity. We covered this earlier, but it needs to be pressed harder here. Unitarity is not just a mathematical nicety about vectors in Hilbert space. It is the guarantee that the equations of quantum mechanics can be run in both directions. It is what makes the past recoverable from the present. If information is destroyed if two distinct initial states can evolve into the same final state, which is exactly what information destruction means, then the evolution is no longer reversible. Different pasts produce identical presents. The mathematics cannot be inverted. Unitarity is gone. That is the first break. But it does not stop there. Susskind, Banks and Peskin worked through the downstream consequences in the early 1980s, and what they found was not subtle. A violation of unitarity, even a small one, does not sit quietly in its corner. It propagates. It infects the structure of the theory in ways that are not containable. Here is one of them. Quantum mechanics, when combined with special relativity, produces quantum field theory. Quantum field theory is what we use to calculate everything from the behavior of electrons in atoms to the decay rates of exotic particles in accelerators, and it works with a precision that is genuinely difficult to overstate. Predictions matching measurements to 10 or 11 decimal places, which is the kind of agreement that makes the theory's foundations feel very solid underfoot. That solidity depends, in a deep way, on unitarity. The probability amplitudes that quantum field theory calculates, the numbers that tell you how likely each possible outcome is, are only probabilities, in the sense of being real numbers between 0 and 1 that sum correctly. If the underlying evolution is unitary, lose unitarity and the amplitudes stop being probabilities, they can become negative, they can exceed 1, they describe nothing physical. Every calculation in quantum field theory, every prediction that has been confirmed to 11 decimal places, rests on a foundation that information destruction knocks out. That is the second break. Still not done. Susskind and his collaborators showed something more specific. A theory with even a small violation of unitarity either generates non-local interactions, correlations between regions of spacetime that are space-like separated, meaning no signal travelling at or below the speed of light could connect them, or it violates energy momentum conservation in large and unacceptable ways. Neither of these is a mild anomaly you could absorb into an error bar somewhere. Non-local interactions of this kind would mean that events in one region of space could instantaneously influence events in a completely disconnected region. Causality, which is the principle that causes precede effects, and that the future cannot reach back and alter the past, starts to come apart. Energy momentum conservation violated at detectable scales would be, very simply, incompatible with every experiment ever performed. So the stakes are quantum mechanics, quantum field theory, causality, energy conservation. All of them load-bearing, all of them connected, in ways that took careful work to trace but that are now understood well enough to be confident about, to the single assumption that information is preserved. Pull the thread of information loss and the fabric does not just snag, it goes. I find myself, and I want to be honest about this, because I think it matters, I find myself slightly suspicious of arguments that say, this assumption must be true because its violation would destroy everything. That kind of reasoning can be self-serving. Physics has been wrong about load-bearing assumptions before. Absolute time felt load-bearing before special relativity. Continuous determinism felt load-bearing before quantum mechanics. The history of the subject is partly a history of discovering that things which seemed untouchable were not. But there is a difference between an assumption being load-bearing in a philosophical sense and being load-bearing in the specific, traceable, calculable way that unitarity is. Susskind, Banks and Peskin were not making a general argument about elegance or aesthetics. They were doing the algebra and showing where the divergences appear, showing which quantities blow up and by how much and why. That is a harder kind of argument to dismiss. The black hole information paradox is not a puzzle about what happens to information when something exotic occurs at the edge of our instruments. It is a puzzle about whether the entire mathematical framework that describes physical reality at its most fundamental level is consistent. Whether the story physics tells about the universe is a story that makes sense all the way through, or whether there is a place where it quietly stops making sense and the pages have been left blank. A particle fell into a black hole. The black hole evaporated. The radiation that came out was thermal. If that is the complete account, then something in the framework is broken, not bent, not strained. Broken in the structural sense, the sense where the load it was carrying can no longer be carried, and the things that depended on it are no longer standing. That is what losing means here. There is an assumption so basic that it rarely gets staked. Information lives inside things. The contents of a box are in the box, not on its surface. The state of a gas is distributed through its volume. Every molecule at its position, moving with its velocity, carrying its energy through the three-dimensional space the gas occupies. The information needed to describe a system scales with how much of it there is, which means it scales with volume. More stuff, more space, more information required. This is deeply intuitive, and it is, in the context of everyday experience in classical physics, completely correct. Jacob Bekenstein found a reason to doubt it. He was working in the early 1970s on the thermodynamics of black holes, which was itself a somewhat unusual thing to be doing, since black holes had only recently been taken seriously as physical objects rather than mathematical curiosities, and their thermodynamic properties were not obviously a productive thing to examine. But Bekenstein was bothered by a specific problem. The second law of thermodynamics says that the total entropy of a closed system never decreases. Entropy, loosely, is a measure of disorder, of the number of ways a system's components could be arranged while still appearing the same from the outside. The second law is stubborn and universal, and physicists treat it with a kind of hard-won respect. The problem: if you throw a hot gas into a black hole, the entropy of the gas disappears behind the horizon. From the outside, the universe appears to have lost entropy. The second law applied to the observable universe appears to be violated. Bekenstein's response to this was not to accept the violation. His response was to ask whether black holes themselves carry entropy, and if so, how much. The answer he found was not what anyone expected. The entropy of a black hole is not proportional to its mass, not proportional to its volume. It is proportional to the area of its event horizon, the two-dimensional surface that marks the boundary between the interior and the exterior. A black hole with twice the horizon area has twice the entropy, regardless of what that area encloses, regardless of the volume inside, regardless of what fell in and when. The relationship is exact, and it is strange, and it was as when Bekenstein proposed it, not immediately welcomed. Hawking initially resisted it, partly because entropy implies temperature, and temperature implies radiation, and classical black holes do not radiate. The circularity bothered him. It was only after Hawking performed his own quantum calculation and found that black holes do in fact radiate, thermally at a temperature inversely proportional to their mass, that the Bekenstein entropy became fully grounded. The two results fit together. The temperature Hawking calculated and the entropy Bekenstein proposed are related by exactly the formula thermodynamics requires. The Bekenstein-Hawking entropy formula, in its final form, says that the entropy of a black hole equals its horizon area divided by 4 times the Planck area, roughly 1 bit of information per Planck scale patch of the event horizon surface. The Planck area is approximately 2.5 times 10 to the power of negative 70 square meters. Horizon areas for realistic black holes are enormous measured in these units. The information capacity implied is correspondingly vast, but the geometry of it is the thing that keeps pulling at me. The information is on the surface, not in the interior. On the boundary, the two-dimensional skin of the object, encoded at a density determined by the most fundamental length scale in physics. Everything the black hole contains, every particle that fell in, every quantum state, every entanglement relationship, is somehow represented in the area of the horizon, not in the volume it encloses. This is where the analogy to a label on a box becomes genuinely insufficient, because a label is added to a box from outside and contains only what someone chose to write on it. What Bekenstein's result suggests is stranger, that the surface is not a label but a complete encoding that reading the surface with sufficient precision would give you the interior, that the interior is not where the information lives but where it is expressed, or, and I want to hold this carefully because I'm not sure these two descriptions are as different as they sound, maybe the interior and the surface are not two separate things with information distributed between them, but one physical situation described from two perspectives, and the perspective that turns out to be fundamental is not the one that fits inside human intuition. The result was strange enough that many physicists were slow to take it seriously. It did not fit. It violated the assumption so basic that stating it had seemed unnecessary. Information lives inside things. Volume is what matters. 3 dimensions, not 2. And here was a calculation, careful and grounded in real thermodynamics and quantum mechanics and general relativity, saying that for the most extreme objects in the universe, the surface knows everything the volume contains. Not more than the volume, everything the volume contains. That crack in the intuition, specific, mathematical, undeniable, is what the next ideas grew from. You have probably held a hologram, a credit card, a sticker, something with that particular shimmery quality that shifts as you tilt it, Not a photograph, not a flat image, but something that seems to contain depth, to present different faces of an object depending on the angle you view it from. If you have looked at one carefully, you may have noticed something odd about it. The depth is not there. The surface is flat. There is no actual recession into the card, no physical three-dimensional object sitting inside the plastic. What is there is an interference pattern, a microscopic arrangement of ridges and variations encoded across the two-dimensional surface, and when light hits it at the right angle, that pattern reconstructs the appearance of three dimensions. The three-dimensional information was encoded on a two-dimensional surface. The surface was sufficient. The volume was not needed. Gerard 't Hooft, in 1993, proposed that the universe might work the same way, not as a metaphor, as a physical claim. The reasoning grew directly from Bekenstein's entropy result. If the maximum information content of a black hole scales with the area of its horizon, rather than its volume, if a sphere of space contains no more information than can be written on its surface, then perhaps this is not a special property of black holes. Perhaps it is a general property of space. Perhaps any region of space bounded by any surface contains no more information than can be encoded on that boundary at a density of roughly 1 bit per Planck area. This is the holographic principle. Leonard Susskind developed and sharpened it through the mid-1990s, partly in response to 't Hooft and partly in response to the black hole information paradox, which had been pressing on him since his disagreement with Hawking began in 1981. The principle, as Susskind articulated it, is not a vague suggestion about analogies between physics and optical tricks. It is a precise quantitative claim. The number of independent physical degrees of freedom in any volume of space is bounded by the area of the surface enclosing it, measured in units of the Planck area, which is approximately 2.5 times 10 to the negative 70 square meters. 1 bit per Planck area, that is the density, that is the resolution at which information is written on the boundary of any region of the physical world. To feel what this implies, consider a sphere 1 meter across, roughly the size of a large beach ball. Its surface area is about 12.5 square meters. In Planck units, that is an area of roughly 5 times 10 to the power of 69 Planck areas. The holographic bound says this region of space can contain no more than that number of bits of information, no more than roughly 5 times 10 to the 69 independent physical facts. That is an almost incomprehensible number by ordinary standards, but it is finite. The information content of any bounded region of space is finite, and it is determined by the area of its boundary, not by its volume. The volume in this picture is, I want to say secondary, but that is not quite right because the interior is real and physical and things genuinely happen inside it. What the holographic principle says is not that the interior is an illusion, but that the interior's information content does not exceed the surface's information capacity. The surface is sufficient to encode everything. Not more than everything, everything. Now this is the point where the hologram analogy starts to become a liability rather than an asset. A hologram on a credit card is an encoding we made. Someone constructed the interference pattern deliberately, using lasers and photographic plates in a process that requires knowing in advance what you want to reconstruct. The reconstruction requires specific illumination conditions. The analogy suggests a deliberate process, an encoder, a decoder, a technology applied to information from outside. The holographic principle is not like that. It is not saying that someone encoded the universe's interior information onto its boundary. It is saying that the physics of the universe is such that the boundary and the interior are not two separate things with information distributed between them, but two descriptions of the same physical situation, and the boundary description is in some sense complete. The interior does not contain more information than the boundary. The interior might, in some deep sense that the mathematics is still working out, be what the boundary looks like from a particular perspective. This is where I find myself wanting to say something careful, and instead not quite finding the right framing. The holographic principle is not proven in the way that a theorem is proven. It is supported by the Bekenstein entropy calculation. by consistency arguments about thought experiments involving black holes and entropy, and most concretely by the ADS/CFT correspondence that Maldacena would propose in 1997, which we will read shortly. But as a general statement about all of space, not just anti-de Sitter space, it remains a principle rather than a derived result. A well-supported, seriously held, technically grounded principle, not a metaphor, not a speculation, but also not yet a theorem. What it does, even held at this level of confidence, is something important for the question we started with. It says that when a particle annihilates inside a volume of space, when photons are produced and then absorbed, when information appears to collapse into an inaccessible interior, the boundary of that region is not passive. The boundary encodes. The surface, if you could read it with sufficient precision, would contain, must contain, if the principle holds, everything happening inside. The information is not trapped in the interior. It was never only in the interior, it was always also on the wall. It started in a room in San Francisco, a conference organized by Werner Erhard, not a physicist, a self-help entrepreneur, which gives the setting a slightly unlikely quality for what turned out to be one of the more consequential meetings in late 20th century theoretical physics. Stephen Hawking was there, Leonard Susskind was there, and Hawking, in the way he had developed of presenting ideas with a directness that left little room for the usual academic softening, told the room that information is lost in black holes, that when matter falls past an event horizon and the black hole eventually evaporates, the information it carried is simply gone, permanently, irrecoverably. Susskind heard this and felt something he later described as a visceral wrongness, not disagreement in the polite sense, not the mild friction of one physicist preferring a different interpretation of ambiguous data, something more uncomfortable. A sense that what Hawking was proposing, if true, would require quantum mechanics to be fundamentally broken in a way that nothing else suggested it was broken. He did not say this loudly in the room. He thought about it on the way home, then he thought about it for the next 20 years. The position Hawking held was not unreasonable, and it is worth being clear about that, because the story is sometimes told as if Hawking was being stubborn or obtuse, and he was neither. His calculation was correct, as far as anyone could determine. The radiation was thermal. Thermal radiation carries no information. A black hole that evaporates completely, leaving only thermal radiation behind, produces a final state that is independent of its initial state. Two black holes formed from completely different infalling matter could, by this account, produce identical radiation. The past would not be recoverable from the present. Unitarity would be violated. Hawking's position was, quantum mechanics must be modified to accommodate this. Information loss is real. The modification will eventually be understood. Most physicists through the 1980s and into the 1990s sided with Hawking. This is the part of the story I find most interesting. Not the conflict itself, but the distribution of initial sympathies. General relativists, almost without exception, found Hawking's position natural. They were accustomed to the event horizon as a real boundary with real consequences, accustomed to the singularity theorems that said certain information was genuinely inaccessible once certain conditions were met. Information loss felt to them like the expected behavior of a spacetime with the topology of a black hole. Particle physicists and quantum field theorists were more troubled, but even many of them were willing to entertain the idea that quantum mechanics might require revision at energies and scales that had never been tested. The theory was always expected to be incomplete somewhere. Maybe this was the somewhere. Susskind's objection, shared by a small number of others, including Gerard Tooft, was not that Hawking's calculation was wrong. It was that the conclusion was unacceptable regardless of the calculation, because the conclusion violated a principle so structurally central that revising it would not produce a modified quantum mechanics, but would produce something that was no longer coherent physics. The argument with Banks and Peskin made this explicit. Unitarity violation doesn't give you a slightly broken quantum mechanics. It gives you a theory that predicts negative probabilities and non-local causation, which is not a theory at all. But this argument, however logically compelling, was not sufficient. It showed that the conclusion was bad. It did not show where the calculation was wrong. And without a specific technical identification of the error in Hawking's reasoning, the objection remained philosophical, persuasive to some, insufficient to most. The years that followed were not comfortable ones for the minority position. Susskind has described the experience of holding an apparently correct argument that nearly no one accepted as genuinely isolating in a way that the cheerful retrospective accounts of scientific controversy tend to understate. He was not ignored, his work was read and engaged with, but the consensus was not moving, and the consensus in theoretical physics is a heavy thing to push against without new mathematics. What changed it gradually was not a single argument but an accumulation. Black hole complementarity, developed by Susskind with Laros Thorlakius and John Uglum in the early 1990s, proposed a specific mechanism by which information could escape without any single observer witnessing a violation of physics. The idea was subtle and initially controversial, but it shifted the conversation from "is information lost" to "by what mechanism might it not be?" Then 't Hooft's dimensional reduction argument, then the Bekenstein entropy calculation being taken with increasing seriousness as the ADS/CFT correspondence began to emerge. Each piece did not win the argument. Each piece made the minority position slightly less uncomfortable to hold. There is something worth sitting with in the sociology of this, which is that the side that turned out to be correct was the one that was outnumbered for most of the debate. The calculation that seemed to show information loss was technically sophisticated and peer-reviewed, and performed by one of the most gifted physicists of the century. The objection was structural and logical, but initially lacked a competing calculation to put alongside it. Physics is not a democracy, and arguments are not settled by votes. But influence and consensus and the willingness of talented people to work on a problem are not irrelevant to how questions get resolved. The information debate took 30 years, partly because the technically correct position had fewer people working on it for a long time. The resolution, when it began to arrive, came not from disproving Hawking's calculation, but from building something around it. A framework in which the calculation could be correct at one level of description while information was simultaneously preserved at a deeper one. That framework had a name. It came from a young Argentine physicist working in Princeton, and it arrived in 1997. Juan Maldacena was 29 years old when he wrote it. The paper appeared in November 1997, submitted to the Archivaj preprint server before formal publication, and it circulated through the theoretical physics community with a speed that papers rarely achieve, which is itself a kind of signal. When something genuinely changes the terms of a conversation, people feel it before they can fully articulate what they are feeling. The paper accumulated citations the way certain ideas accumulate attention, not through aggressive promotion, but through the particular gravity of a result that keeps turning out to be relevant to things you were already thinking about. It has since become the most cited paper in the history of high-energy physics, by some counts over 15,000 citations. For context, most influential physics papers accumulate dozens, occasionally hundreds. The gap between those numbers and 15,000 is not a matter of degree. What did it say? The setting is a specific type of spacetime called anti-de Sitter space, which is a solution to Einstein's field equations with a negative cosmological constant, a universe that is, in a precise mathematical sense, curved like a saddle rather than like a sphere. Anti-de Sitter, space has a property that distinguishes it from the universe we actually inhabit. It has a boundary. Not a boundary in the sense of a wall or an edge where space stops, but a boundary in the conformal sense, a surface at infinity that the geometry of the space defines in a mathematically rigorous way. Maldacena's conjecture, a theory of quantum gravity in the interior of an anti-de Sitter space, specifically type 2b string theory on a 5-dimensional anti-de Sitter space crossed with a 5-sphere, is exactly equivalent to a specific quantum field theory living on the 4-dimensional boundary. Not approximately equivalent. Not equivalent in some limiting case or under certain conditions. Exactly, completely, in every detail equivalent. The two theories are dual descriptions of the same physical situation. The The boundary theory is a conformal field theory, a specific one, four-dimensional super Yang-Mills theory with a particular symmetry structure. And this theory is, by construction, a standard quantum field theory operating on a fixed background. It is manifestly unitary, not assumed to be unitary, not unitary in some approximate or emergent sense, unitary in the hard structural definitional way that any well-constructed quantum field theory is unitary. The Hilbert space is well defined. The evolution operator is unitary. Probabilities sum to 1. The past is recoverable from the present. Now apply the equivalence. If the boundary theory and the bulk theory are exactly equivalent, then anything true of one must be true of the other, including unitarity. The bulk theory, the gravitational theory inside the anti-de Sitter space, the theory in which black holes can form and evaporate and Hawking radiation can be produced, must be unitary, because its equivalent description on the boundary is unitary. There is no room for information destruction in the bulk theory, because information destruction would make the bulk theory non-unitary, and the boundary theory is already unitary, and they are the same theory. This is not a detailed mechanism. Maldacena's paper does not explain how information escapes a black hole in the bulk description, does not trace the specific path by which information encoded in infalling matter gets encoded in Hawking radiation. It is not that kind of result. It is more like, and I am going to reach for an analogy here carefully, it is more like proving that a particular room cannot contain a certain kind of object by showing that the architectural constraints of the building make the object's presence impossible, without specifying exactly where the object went instead. The bulk theory must be unitary. The information must be preserved. The how remains, at the level of Maldacena's original paper, unspecified. But the what is settled in a way it had not been before. This is what changed the terms of the debate. Before 1997, the argument between Hawking and Susskind was, at bottom, a conflict between a calculation and a principle. Hawking had a calculation showing thermal radiation. Susskind had a principle, unitarity, saying the conclusion was unacceptable. The calculation was concrete. The principle, however well-founded, was abstract in the sense of not being attached to a specific competing calculation. After 1997, the situation was different. Maldacena had a framework, not just a principle, but a mathematical structure with a specific dual description, in which unitarity was not an external constraint being applied to the bulk physics from outside, but an intrinsic property of the dual theory. If you accepted the equivalence, information preservation was not a hope, it was a theorem. Most physicists accepted the equivalence, not because it was proven, it remains a conjecture in the technical sense, meaning it has not been derived from more fundamental principles, though it has been tested in enormous numbers of limiting cases with no failures. But because it was consistent, productive, and connected to so many other results in so many different areas of physics, that its essential correctness became difficult to seriously doubt. Hawking himself apparently found it convincing. He cited the ADS/CFT correspondence as a significant factor in his 2004 Concession, suggesting that the boundary theory's unitarity was the argument that finally moved him more than any of the others. The paper is dense. Reading it without substantial background in string theory and conformal field theory is not a comfortable experience. But sitting inside the idea it contains, once you have spent enough time with it to feel its structure, is something else. The sense that the interior and the boundary are the same description, that the gravitational physics happening in the bulk is being simultaneously and completely and unitarily described by something living on the skin of the space. It is, I think, one of the genuinely strange results of the 20th century. Strange in the way that special relativity was strange, not complicated, not technical in its core claim, but deeply disorienting to the intuition that space and dimension, and inside and outside are simple concepts with stable meanings. They are not apparently as simple as they seemed. Dublin, July 2004. the 17th International Conference on General Relativity and Gravitation. Not a small gathering, not an informal seminar where the stakes of saying something could be managed by the informality of the setting. A proper conference, the kind where the program is printed and the sessions are scheduled and the people in the room have flown from many countries to be there. Hawking had requested time to speak. He had something to announce. He had been working quietly on a new approach to the black hole information paradox. His own approach, distinct from Maldacena's ADS/CFT argument. A calculation involving the path integral over spacetime geometries and the specific contributions of different topologies. The details are technical, and the paper he subsequently submitted was debated and not universally accepted as the definitive resolution he may have intended it to be. But the conclusion he had reached, whatever the mechanism he proposed, was a reversal of the position he had held since 1976. He stood in Dublin and said, "Information is not lost in black holes." The bet he had made with John Preskill in 1997, information destroyed in black hole evaporation, Thorne and Hawking against Preskill, he was ready to concede. He had brought a baseball encyclopedia. The terms of the bet specified that the loser would provide the winner with an encyclopedia of their choice, from which information could be retrieved at will. The symbolism was not accidental, and the room understood it. He gave Preskill the encyclopedia. Preskill has described receiving it as a slightly surreal experience. The object itself, a thick, ordinary reference book sitting in his hands in a conference hall in Dublin, felt inadequate to the moment it was marking. 27 years of one of the most consequential arguments in theoretical physics, and here was a book about baseball statistics. Hawking later joked that he should have given its ashes, since what Preskill really needed was the information in a form that had been scrambled beyond practical recovery. The joke is funny and also, in a way that I think Hawking intended, technically precise. Kip Thorne did not concede. He has not conceded since. This fact tends to get a single sentence in most accounts of the concession, and I think it deserves slightly more attention than that, because it is not a small thing. Thorne is not a casual physicist. His skepticism about information preservation, sustained through Hawking's concession and through the accumulation of ADS/CFT evidence, and through everything that followed, reflects a genuine and unresolved tension in how general relativists and quantum field theorists weight different kinds of evidence. What Hawking's concession settled, and what it did not settle, is worth being precise about. It settled in the sense of shifting the consensus of the physics community, the basic question of whether information is preserved or destroyed. After 2004, the majority position, already moving in this direction through the 1990s under the influence of ADS/CFT, became that information is preserved. Unitarity holds. The apparent destruction implied by Hawking's original calculation is an artifact of the approximations involved, not a feature of the underlying physics. What it did not settle is the mechanism. How does the information get out? Where exactly does the calculation break down that Hawking performed in 1974? At what point in the evaporation process does the information begin to emerge in the Hawking radiation? And in what form? And through what specific physical process? These questions remained open in Dublin. They remain in their details, open now. This is the part that tends to get glossed over in accounts of the concession, because a concession feels like an ending, and the story of the information paradox is more satisfying with an ending. But physics does not always provide those. Hawking conceding that information is preserved is an important moment. It is not a derivation of the mechanism. It is not a full solution. It is the acknowledgement by the person who posed the sharpest version of the problem that the answer his own calculation implied was wrong. The conference moved on. Other talks were given. The encyclopedia sat somewhere, or was shelved, or is in a box in Preskill's office. I do not know, actually, what became of the physical object. and there is something slightly funny about not knowing the precise location of an encyclopedia given as the symbol of information retrieval. The real argument about the mechanism was just getting started. Dublin was not an ending. It was the moment when the question became officially a different question. Not whether information survives, but how. Don Page had a specific question, not the general question of whether information is preserved. He'd already decided, on the basis of unitarity, that it must be. His question was narrower and more diagnostic. If information is preserved during black hole evaporation, what should the entropy of the Hawking radiation look like as a function of time? What shape should that curve take, and how would it differ from the shape Hawking's calculation predicted? He worked this out in 1993, and the result was clean enough to become the central benchmark for every serious attempt at a solution that followed. Start with what entropy means in this context. Von Neumann entropy, the quantum mechanical version of entropy relevant here, measures how entangled a system is with its environment, or equivalently how much information about the system is unavailable if you only have access to the system itself and not everything it is entangled with. A pure quantum state has zero von Neumann entropy. A maximally mixed state has its entropy equal to the logarithm of the number of possible states. These are the two extremes. A black hole begins in a pure state. The matter that collapsed to form it had a definite quantum state, complex, entangled with many things, but pure in the sense that its complete description is in principle available. The von Neumann entropy of the black hole, at the moment of formation, is zero, or close enough to zero that the distinction does not matter for what follows. Now the black hole begins to radiate. Hawking radiation carries energy away from the black hole, slowly, continuously. Each emitted particle is entangled with the particles that remain inside, the partner that fell inward when the virtual pair separated at the horizon. The radiation accumulates outside, the black hole slowly loses mass. Here is what Hawking's calculation predicts for the entropy of the radiation. It rises continuously. Each new particle added to the radiation increases the total entanglement between the radiation and the remaining black hole interior. The entropy climbs and climbs, and when the black hole has fully evaporated, when the last particle has been emitted, and there is nothing left and the entropy of the radiation is at its maximum. That final state is the problem. The black hole is gone. There is nothing left for the radiation to be entangled with, but the radiation has high entropy, which means it is highly mixed, which means it is entangled with something. A maximally mixed state of radiation, with no remaining black hole to be the other side of the entanglement, is, in quantum mechanical terms, a deeply incoherent situation. The entropy should be zero at the end, because the total system began as a pure state, and pure state evolution is unitary and unitarity preserves purity. But Hawking's curve says maximum entropy at the end. The curve never turns around. Page's prediction, by contrast, has a shape. The entropy of the radiation rises initially. This part matches Hawking's calculation, and for good reason, because in the early stages of evaporation, when the black hole is large and most of the information is still inside, each new emitted particle genuinely does increase the entanglement between radiation and interior. The radiation is accumulating, the black hole is barely smaller, and the entropy growth is real. But at some point, the Page time, which occurs roughly when the black hole has lost half its initial entropy, which is not the same as half its mass and occurs considerably earlier, the curve peaks and turns. After the Page time, each new Hawking particle carries not just new entanglement, but also correlations with the previously emitted radiation. The information that was stored in the black hole begins to leak out, encoded in the subtle correlations between early and late radiation. The entanglement entropy of the radiation decreases. It does not decrease quickly, but it decreases. By the time the black hole has completely evaporated, the entropy of the radiation has returned to zero. The radiation is in a pure state. All the information that fell in has come back out, scrambled almost beyond recognition in the correlations between millions of individually thermal-looking particles, but present. The shape is called the page curve, a rise, a peak, a fall, symmetric in entropy if not in time, since the page time occurs much earlier than the halfway point of the evaporation process in terms of duration. Two curves then, Hawking's, which rises monotonically to a maximum and stays there, Page's, which rises and falls back to zero. The difference between them is not subtle or ambiguous. It is a qualitative difference in the behaviour of the entropy at late times, which corresponds to a qualitative difference in the physical situation. Either information survives the evaporation or it does not, and the two possibilities produce curves with different shapes. Reproducing the page curve from a calculation, not assuming it, not deriving it from a boundary theory where unitarity is already built in, but actually showing from the physics of the bulk that the entropy turns around at the page time, became the standard by which any proposed solution would be judged. It is a diagnostic, a test. Not the only test, but the most specific and demanding one, because it requires getting not just the qualitative answer right, but the quantitative shape. For 26 years after Page described the curve, no one could produce it from a direct calculation in the bulk. Then in 2019, two groups did. Two papers appeared in 2019, submitted within weeks of each other, by groups working independently. Jeffrey Pennington at Stanford, Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield spread across several institutions. Neither group knew, or knew fully, what the other was doing. Both arrived at the same result, which is the kind of convergence that physics takes seriously, not because simultaneous discovery is unusual, but because independent arrival at the same specific mathematical structure from different starting points is a strong signal that the structure is real. What they derived was the page curve, not assumed, not borrowed from the boundary theory's unitarity, derived using a semi-classical calculation in the bulk, a calculation that takes gravity seriously but treats it as approximately classical, while keeping the quantum mechanics of the matter fields fully quantum. The entropy of the Hawking radiation, computed this way, rises, reaches a maximum around the page time, and falls back to zero as the black hole completes its evaporation. The mechanism that produces this behaviour is called the island formula, and the thing it introduces, the thing you have to add to the entropy calculation to get the right answer, is an island. Let me try to say what an island is carefully, because the word makes it sound simpler and more spatial than the mathematics actually requires. In quantum gravity, the entropy of a region is not computed simply by looking at the quantum fields in that region and asking how entangled they are with the outside. There is a geometric contribution too, a term proportional to the area of the boundary of the region, which is exactly the Bekenstein-Hawking entropy contribution from surfaces within the bulk. The full entropy is the sum of these two pieces, the geometric area term and the bulk entanglement entropy. The surface that minimizes this total is called the quantum extremal surface, and the entropy calculated at that surface is the physically correct entropy to assign to the region. Before the page time, the quantum extremal surface for the Hawking radiation is just what you would expect. It lies near the horizon, and the entropy calculation gives the rising Hawking curve. The island, in this phase, does not appear. The dominant contribution comes from the region outside the black hole, and the entropy grows as more radiation accumulates. After the page time, something changes. A new quantum extremal surface becomes available, one that encloses not just the exterior radiation, but also a region inside the black hole horizon. This interior region is the island. It sits behind the horizon, disconnected in the ordinary spatial sense from the radiation detectors outside, and yet the entropy calculation that includes it gives a lower total entropy than the calculation without it. Lower total entropy means this is the correct surface to use, by the rule that the quantum extremal surface is defined as the one that minimizes the entropy. The island is the region of the black hole interior whose information is encoded in the Hawking radiation. This is I want to be careful here, because the temptation is to make it sound more resolved than it is. This is a strange and somewhat vertiginous claim. The island is behind the horizon. Nothing can travel from the island to the radiation detectors in the ordinary sense. No signal, no particle, no photon. Moving at the speed of light can get from inside the event horizon to outside it. And yet the island's information content is, according to this calculation, already encoded in the radiation that has escaped. Not because it travelled out, because the entanglement structure of the system is such that the interior and the exterior radiation are not independent descriptions. The island's information is in the radiation the way the answer to a question is in a key that you already hold, not transmitted in the moment you notice it, but present in a relationship that was established earlier, and whose implications you are only now working out. The word island is, I think, slightly misleading in a way worth acknowledging. It suggests a piece of land surrounded by water, isolated, contained, reachable only by crossing the surrounding medium. The island in this calculation is not reachable from outside in any ordinary sense. What the name captures is the separateness of the region, the fact that it's a discrete piece of spacetime that gets included in the entropy calculation, not because it is connected to the exterior by a classical path, but because the entanglement structure of the quantum state makes it part of the radiation's description. After the page time, the island grows. More of the black hole interior falls inside the island's boundary, as the black hole continues to evaporate. More interior information becomes encoded in the exterior radiation. The entropy of the radiation, rather than growing as it accumulates more particles, now falls, because the island's contribution to the entropy calculation is shrinking the total, pulling the curve downward towards zero. At the end of evaporation, the island has swallowed the entire interior. The black hole is gone. The radiation is in a pure state. The entropy is zero. What this implies about the geography of information is not entirely comfortable to sit with. The interior of the black hole is not, and I am going to allow myself to admit that this is where my confidence about how to describe things becomes genuinely shaky. The interior of the black hole is not simply a separate region of space-time whose contents are hidden behind a horizon. After the page time, it is a region whose informational content is encoded in the exterior, in the radiation that has already escaped, in a way that makes the boundary between inside and outside less like a wall and more like a coordinate choice that the quantum state does not fully respect. The island formula does not tell us how this works. It does not provide a space-time picture of the mechanism. It provides a rule. Compute the entropy this way, include the island contribution, get the correct answer, without fully specifying the physical story beneath the rule. That physical story is still being worked out. The island appeared in the calculation. What it means for the geometry of the black hole interior, for the experience of something falling through the horizon after the page time, for the relationship between the radiation and the region it encodes, these questions were not settled by the 2019 papers. They were sharpened by them, which is in physics often what a breakthrough does. Not close the question, bring it into focus. The concession was 8 years old. The ADS/CFT argument was settled enough that most physicists had moved on to working within the framework rather than arguing about it. The page curve was the acknowledged target. The information paradox felt, if not solved, at least located. The answer was unitarity. The answer was holography. The mechanism would eventually be worked out. There was still work to do, but the direction was clear. Then 4 physicists looked carefully at what unitarity actually requires of the region just outside the horizon, and found something that had been sitting in the mathematics the whole time, unexamined. The 2012 paper by Ahmed Al-Meheri, Donald Marolf, Joseph Polchinski, and James Sully, AMPS by their initials, did not question whether information is preserved. It accepted that. It accepted unitarity. It accepted the ADS/CFT evidence. It started from those acceptances and asked what they imply about the physical experience of the event horizon, and arrived at a conclusion that made the problem considerably harder than it had appeared. The argument begins with a property of quantum entanglement called monogamy. Entanglement, unlike most things, cannot be shared without cost. If two quantum systems are maximally entangled with each other, if they share the strongest possible quantum correlation, then neither of them can be entangled with anything else, at all. The maximum entanglement with one system uses up the entire entanglement budget. This is not a practical limitation. It is a mathematical theorem about the structure of quantum states. Now consider an old black hole, one that has evaporated past its page time, so that more than half of its original entropy has been radiated away. At this stage, unitarity requires that the recently emitted Hawking radiation be entangled with the previously emitted Hawking radiation. This is how information gets out. The late radiation carries correlations with the early radiation that, taken together, encode the information that fell in. If the late radiation is not entangled with the early radiation, the entropy never turns around, the page curve is not reproduced, information is destroyed. Unitarity demands this entanglement. But quantum field theory in curved spacetime, the framework that describes what a freely falling observer experiences near a black hole horizon, requires something different. It requires that each Hawking particle be entangled with its partner inside the horizon. This is how the radiation is produced. Virtual pairs separate at the horizon, one particle escaping and one falling in, and the two are entangled with each other. The horizon being smooth, the equivalence principle being satisfied, the infalling observer experiencing nothing dramatic at the moment of crossing, depends on this interior entanglement being intact. So the late Hawking radiation must be maximally entangled with the early radiation, and it must be maximally entangled with its interior partner. And monogamy says it cannot be maximally entangled with both simultaneously. One of the three assumptions must break. A MPS laid them out clearly. First, unitarity holds, information escapes, the page curve is correct. Second, the horizon is smooth, no drama, no detectable physical effect at the moment of crossing. The equivalence principle is satisfied for an infalling observer. Third, quantum field theory works correctly in the vicinity of the horizon, which is a region of low curvature where there is no obvious reason for it to fail. All three are reasonable. All three have strong independent support. And they cannot all be simultaneously true for an old black hole. The mathematics is, as far as anyone has been able to determine, correct. A MPS argued that the most conservative resolution was to sacrifice the second assumption. If the late radiation must be entangled with the early radiation rather than with its interior partner, then the interior partner is not in the usual Hawking vacuum state. The horizon is not smooth. Instead, the entanglement between the outgoing particle and its would-be interior partner is broken, and the interior partner is in a high-energy state. A wall of energetic quanta sitting just inside the horizon, burning anything that attempts to fall through. A firewall. This is genuinely uncomfortable in a way that goes beyond the technical. The equivalence principle, Einstein's foundational idea that a freely falling observer cannot locally distinguish between free fall in a gravitational field and free fall in empty space, would be violated at the horizon. Not in some distant quantum gravity regime, not at the singularity where curvature is extreme and no one expected classical physics to hold, but at the horizon of a large black hole where the curvature is mild and everything classical says nothing special should happen. The firewall makes the horizon a physically dramatic place. An infalling astronomer, perhaps one who studied physics and understood that classical general relativity predicts a smooth crossing, would, on AMPS's account, be incinerated the moment they crossed. Not by anything the classical theory predicted, by the quantum mechanical requirements of unitarity and monogamy. There is something so almost philosophically disagreeable about this conclusion, and I noticed that disagreement in myself without being able to immediately distinguish how much of it is intuition pointing at something real, and how much of it is just discomfort with a counterintuitive result. The firewall paper provoked an enormous response. Dozens of papers appeared within months. proposing resolutions, questioning assumptions, suggesting modifications to quantum mechanics or to the equivalence principle, or to the way entanglement monogamy applies in this context. The ER equals EPR conjecture, which we will reach shortly, was partly a response to this. The island formula, derived 7 years later, recovers the Page curve but does not by itself definitively address what happens at the horizon. The firewall is not resolved, not in the sense that a clear consensus has formed about which assumption breaks and why, and what the physical picture looks like on the other side of that breaking. The 2012 paper opened something that the subsequent decade of work has clarified and deepened, but not closed, which puts it in an unusual position for something this specific: known, unresolved, both. In 1935, Einstein published 2 papers. They were not connected at the time in any way he recognized or noted. The first, written with Nathan Rosen, described a solution to the general relativity field equations in which 2 regions of spacetime are connected by a bridge, a tunnel through the geometry of space linking 2 distant points without requiring a path through the space between them. Einstein and Rosen were trying to construct a model of elementary particles from the geometry of spacetime itself, and the bridge was a byproduct of that attempt. It did not work as a particle model. The bridges, later called Einstein-Rosen bridges, and later still called wormholes, were noted and mostly set aside. The second paper, written with Boris Podolsky and Rosen, described what happened when 2 particles interacted and then separated, carrying between them correlations that seem to resist any local explanation. Measure one particle's spin and the other particle's spin is instantly determined, regardless of the distance between them. Einstein found this troubling, thought it implied quantum mechanics was incomplete, called the correlation spooky. The paper became one of the most discussed in the history of physics, not because Einstein's preferred conclusion was correct, it was not, but because the phenomenon it described, which came to be called quantum entanglement, turned out to be real and fundamental and considerably stranger than even Einstein had appreciated. 2 papers, 2 phenomena. No connection stated or implied. 78 years later, Juan Maldacena and Leonard Susskind proposed that they were the same thing. The conjecture is called ER equals EPR, after the 2 1935 papers. Einstein-Rosen bridges equal Einstein-Podolsky-Rosen pairs. Wormholes equal entanglement, not similar, not analogous. The same physical phenomenon described in 2 different languages. The motivation was the firewall paradox. If entangled Hawking particles, the one that escapes and the one that fell inside, are maximally entangled with each other, a monogamy of entanglement creates the crisis AMPS described, then perhaps the resolution is that the entanglement between an escaping Hawking particle and its interior partner is not a correlation across empty space but a geometric connection, a microscopic wormhole. The 2 particles are entangled because they are connected by an Einstein-Rosen bridge, a bridge so small and so non-traversable that nothing can pass through it, but real enough to carry the entanglement relationship that the quantum state requires. In this picture, the crisis dissolves. The late Hawking radiation is entangled with the early radiation. This is required by unitarity, and it holds. The escaping particle is connected to its interior partner by a wormhole. This is required by the smoothness of the horizon, and it also holds. The apparent violation of monogamy disappears because the 2 entanglements are not competing for the same resource. They are, in some sense, that the mathematics is still working out. Different aspects of the same geometric structure. This is, I want to say it is elegant, and it is, but I also want to be careful about allowing elegance to substitute for verification, because the conjecture remains unproven in the rigorous sense. What it has is consistency, and a remarkable amount of it. Every check that has been performed, and there have been many across many different corners of quantum gravity and holography and quantum information theory, has found no contradiction. But the deeper implication, which extends far beyond the firewall paradox, is what makes ER equals EPR something more than a proposed resolution to a specific technical crisis. If entanglement is wormholes, if every pair of entangled quantum systems is connected by a geometric bridge, then the structure of spacetime is not the foundation from which quantum mechanics emerges, it is the other way around. Spacetime geometry is a consequence of entanglement. The connectedness of space, the fact that distant regions are parts of the same continuous manifold rather than isolated patches, with no relationship to each other, is built from the web of quantum correlations threading through the quantum state of the universe. Maldacena said it directly: without entanglement, space-time would atomize. The geometric fabric, the smooth, continuous, navigable space that we move through and that holds the objects we interact with, is held together by entanglement. Cut the correlations and the space comes apart. The wormholes are what keep distant regions of space in contact with each other, and the wormholes are entanglement, and entanglement is everywhere. This is where the fabric image becomes genuinely useful rather than merely decorative. Space-time as fabric is a cliché so worn it barely registers anymore, usually invoked to explain how mass curves the geometry around it. But if ER equals EPR is correct, the fabric metaphor earns its place in a different sense. The threads are entanglement, and the weaving is the wormhole structure, and what we call space is the pattern that emerges when those threads are arranged in the particular way the quantum state of the universe arranges them. Pull out enough threads, break enough entanglement, and the fabric does not stretch or distort. It stops being fabric. This changes the meaning of the information question we started with. If a particle annihilates and its information is carried away by entangled photons, what is happening geometrically is not just that two particles fly apart carrying correlated quantum states. It is that two regions of space-time are being held in a specific relationship by the wormhole structure that the entanglement encodes. The information does not travel through space. It is part of the structure that makes space what it is, whether ER equals EPR is correct in its full generality, whether it applies to all entangled systems or only to specific configurations, whether it genuinely resolves the firewall paradox or merely relocates it, is not settled. Susskind and Maldacena are aware of the limitations of the current formulation. The conjecture is stronger in some regimes than others, but the direction it points, the possibility it raises, is one of the more startling in contemporary physics. Space as consequence. Geometry as information. The universe not containing quantum correlations but made of them. Drop something into a large, still body of water. Not a stone, a drop of dye. Something that was concentrated in one place, carrying its colour and its chemical identity in a small, dense volume. Watch what happens. The dye disperses. It spreads through the water in expanding tendrils, thinning as it goes, reaching into regions of the water that were perfectly clear a moment before. Given enough time, the dye is everywhere and visibly nowhere. The water is faintly uniformly coloured. No local sample tells you where the dye entered. No local measurement recovers the original drop. But the dye is there, every molecule of it. Dispersed, yes. Inaccessible to local measurement, yes. Gone in the practical sense of being unretrievable without access to the entire body of water and the ability to track every molecule simultaneously. But not absent, not destroyed. Present in the global distribution of the system in a way that a sufficiently comprehensive measurement could, in principle, confirm. This is scrambling. Not a perfect analogy. The dye in water is classical, and quantum scrambling involves entanglement in ways that classical dispersion does not. But the core distinction it illustrates is the one this chapter is about. Information that is inaccessible is not the same as information that is absent. These two things feel similar. From the outside, from the perspective of any measurement you can practically perform, a system that has scrambled its information and a system that has destroyed its information can look identical. Neither gives you the original. Neither lets you reconstruct the past from a local snapshot of the present. The practical difference between them is zero if your measurement capabilities are bounded, which they always are. But the physical difference is everything. A system that has scrambled its information is still unitary. The evolution is still reversible. The past is still encoded in the present, just encoded in correlations between enormous numbers of degrees of freedom rather than in any local accessible spot. The laws of physics remain intact. Unitarity holds. A system that has destroyed its information is not unitary. The evolution is not reversible. Two different pasts could produce the same present. The laws of physics, in the form we understand them, do not hold. Scrambling is how the universe hides information without losing it. And black holes, according to the best current understanding, are the most efficient scramblers in nature. The timescale for a black hole to scramble in falling information is called the scrambling time, and it is surprisingly short given the black hole's other characteristic timescales. For a black hole with a given entropy S, the scrambling timescales is the black hole's radius times the logarithm of its entropy. For a stellar mass black hole, this is on the order of milliseconds. The evaporation time for the same black hole is something like 10 to the power of 67 years. The black hole scrambles the information it receives almost immediately, in the cosmological sense, and then sits on it, in scrambled form distributed across all its degrees of freedom, for an almost incomprehensible length of time before the information slowly leaks back out in the Hawking radiation. Fast scrambling, slow release. The information is not gone. It is just, and I keep reaching for a word that does not carry the wrong connotations, it is just very thoroughly mixed into the system. Mixed in the quantum sense, which means entangled across every available degree of freedom, encoded in correlations between particles that have no obvious individual connection to the original information, distributed in a way that makes local recovery impossible but global recovery, in principle, merely difficult. Merely difficult is doing a lot of work in that sentence, and I want to acknowledge it. In practice, decoding the information in Hawking radiation would require measuring correlations between an astronomical number of individual photons emitted over a timescale that dwarfs the current age of the universe. The quantum computation required to extract the original information from the scrambled output has been estimated at a scale that makes the word intractable seem mild. No technology we can imagine, no technology we can coherently describe, could perform it. But intractable is not impossible. And impossible is not the claim. The claim, the important claim, the one that keeps physics consistent, is that the information is there. Encoded, scrambled, distributed beyond any practical recovery. But present in the structure of the state. The global measurement that would confirm its presence is not one we can perform. The physics that says the information is there is not dependent on our ability to confirm it. This is the distinction that matters when someone says a black hole destroys information. It does not, if current understanding is correct, destroy information. It scrambles it to an extreme that is practically indistinguishable from destruction, but physically, structurally, mathematically distinct from it. The electron that fell in, the complete quantum state of every particle that ever crossed the horizon, is in the Hawking radiation. And where, c'est? In correlations between particles emitted over billions of years, in phase relationships between photons that individually look thermal, in a global pattern that encodes everything without any local piece of it encoding anything recognizable. The ink is in the water, every molecule. Classical information can be copied. This is so obvious in everyday experience that stating it feels unnecessary. You copy a file, you photograph a document, you read a book, and the information in the book is also now in your memory, and the past book is unchanged. Classical information sits still for duplication. You can make as many identical copies as you want, and nothing in the laws of physics objects to this. The original and the copies are genuinely identical. The act of copying does not disturb the original. This is the comfortable, familiar behavior of information at the scale where human intuition was developed. Quantum information does not do this. In 1982, William Wouters, Wojciech Zurek, and independently Dennis Deeks proved what became known as the no-cloning theorem. The theorem states that it is impossible by any physical process permitted by quantum mechanics to create an exact copy of an arbitrary unknown quantum state. Not difficult, not practically challenging with current technology. Impossible in the mathematical sense that assuming it is possible leads directly to a contradiction with the linearity of quantum mechanics. The proof is not complicated. If a cloning machine existed, a device that takes an unknown quantum state as input and produces two identical copies of it, then you could use it to distinguish quantum states that quantum mechanics says cannot be distinguished, and you could send information faster than light using entanglement, which quantum mechanics also forbids. The cloning machine is not just unavailable, its existence is inconsistent with the structure of the theory. What this means for the particle we have been following is specific and important. Before the electron and positron annihilated, their quantum states were not copied anywhere. Not backed up, not transferred to some safe storage while the original proceeded toward its end. The quantum state of the electron, its spin, its entanglement relationships, its complete specification was in the electron singular and nowhere else. When the annihilation happened, that state had exactly one place to go, into the output of the interaction, into the photons, into the entanglement between them. There was no copy, there could not have been. The no-cloning theorem closes that option completely. But, and this is where the companion theorem matters, the information also could not have been deleted. The no-deleting theorem, proved by Aaron Party and Samuel Bronstein and published in 2000, is in some ways the mirror image of no-cloning. It states that given two copies of an arbitrary quantum state, it is impossible to erase one of them while leaving the other intact. You cannot use a physical process to take a quantum state to a blank state without disturbing the remaining copy. Deletion, like copying, is forbidden by the linearity of quantum mechanics. The no-cloning and no-deleting theorems together describe a world in which quantum information is, I want to use a word here that is accurate without being too dramatic, indestructible is too strong, because it implies something about what the information looks like. And Scrambling shows that the form can change completely. Indelible is closer. Quantum information is indelible. It cannot be duplicated. It cannot be erased. It can be transformed, scrambled, encoded in different physical carriers, spread across many degrees of freedom, made practically inaccessible by any measurement you could perform. But it cannot be made to not exist. The no-cloning theorem is why quantum cryptography works. An eavesdropper cannot intercept a quantum key without disturbing it, because copying it would violate the theorem. The no-deleting theorem is less famous and less applied, but no less fundamental. Together, they are not just results about quantum information technology. They are results about the structure of physical reality. They say that the universe, at its most fundamental level, neither makes copies nor discards originals. No photocopier, no shredder. This is, if you let it settle, a strange thing to know about the world you are living inside. Every quantum state that has ever existed, every electron's spin, every photon's polarization, every entanglement relationship between any two particles that have ever interacted has left a thread in the physical record that cannot be cut. Not because anything is storing it deliberately, because the mathematics of quantum evolution is linear and unitary, and therefore irreversible in the sense that counts, and linearity and unitarity together forbid both copying and deletion. The electron that vanished in Chapter 1 could not have had its information deleted. The theorem forbids it. The information had to go somewhere because it had no other option, not because the universe is careful, not because some mechanism was watching over it, but because the structure of quantum mechanics does not include a way for quantum information to cease to exist. It went into the photons, into their entanglement, into correlations that persist in the electromagnetic field, moving outward at the speed of light, carrying what the electron was in a form that no single measurement will fully reveal, but that no physical process has erased. The universe has no shredder. It never did. We started with an electron, not a type of electron, not a representative example drawn from the category of things called electrons. This particular one, the one from the opening chapter. The one we watched approach its mirror opposite across a shrinking distance and enter a bound state that lasted 125 picoseconds before the wave functions overlapped completely and the annihilation event closed the transaction. That electron, the one that was there and then was not. We have spent a long time since then building the machinery to answer the question that Electron posed, and now the machinery is built, or built enough, and we can go back. The electron had a quantum state. This is not a vague statement. The quantum state of an electron is a precise mathematical object, a vector in a Hilbert space, specifying the probability amplitudes for every measurable property the electron possesses. Its spin orientation, 1/2, pointing in some direction that is itself a superposition of up and down until measured. Its momentum, its position expressed as a wave function smeared across space with a particular shape determined by how it had been interacting with its environment. Its entanglement with other particles it had encountered as, because electrons do not move through the world without touching it. And touching at the quantum level leaves entanglement, and entanglement persists. All of this was the electron, not a description of the electron from outside. The state was the electron, in the sense that the state contains everything that physics considers real about it. Where did it go? The first place to look is the photons. The annihilation produced 2 of them, moving in opposite directions, each carrying 0.511 mega-electron volts of energy. The exact rest mass energy of 1 electron, because energy is conserved and the arithmetic demands it. The photons carry momentum, equal, opposite, summing to the near-zero momentum of the positronium system before the event. They carry angular momentum. The spin configuration of the positronium state is encoded in the polarization relationship between the 2 photons, which are required by conservation to be perpendicular to each other, which means that measuring one determines the other, which means they are entangled in a way that carries the spin information of the original pair forward. The quantum state of the positronium, the combined state of the electron and positron at the moment of annihilation, is present in the joint quantum state of the 2 photons, not approximately, not in some coarse-grained summary. In the full detail that quantum mechanics tracks, the correlations between the photons encode the correlations that existed in the particle pair that produced them. The no-cloning theorem guarantees that this information was not duplicated before the event. The no-deleting theorem guarantees it was not erased during it. The unitarity of quantum evolution guarantees it was transferred completely. The electron's information left with the photons. But the photons are not the end of the story because the photons interact. They travel through space and space is not empty. It is filled with fields, and those fields respond to the photons as they pass, and the photons become entangled with those fields, and the correlation spread. A photon absorbed by an atom transfers its energy and its quantum state information to that atom's electrons, which are now entangled with the field that produced the photon, which is entangled with the other photon, which carries the remainder of the electron's original state information. The information does not sit cleanly in 2 photons moving apart. It propagates into the environment, spreading through every system the photons interact with, becoming distributed across an ever larger network of entangled degrees of freedom. This is scrambling, but at cosmological scale and over cosmological time. The electron's information is not in any one place. It is not findable by measuring any single system. It is in the pattern, the global, comprehensive, practically inaccessible but physically present pattern of correlations between everything the photons have touched and everything those things have touched and everything those things have touched in turn, propagating outward at the speed of light in an expanding sphere of entanglement that by now, depending on when this annihilation occurred, encompasses an enormous volume of the universe. The electron is gone. The electron's information is in the structure of the universe, not metaphorically, in the correlations between quantum states, in the entanglement network that ER equals EPR suggests is also the geometric network that holds spacetime together. In the Hilbert space of the universe, the total quantum state of everything, the electron's fingerprint is present as a constraint on what combinations of other states can occur, because the evolution was unitary, the past is encoded in the present, and the electron was part of the past. I want to be careful here at the end of the tracing not to oversell what this means. The electron's information being present in the universe's quantum state is not the same as the electron being present. The electron is gone. The particle, the localized excitation of the electron field, the specific ripple we followed through 5 chapters, is not there anymore. The field relaxed. The excitation ended. There is no electron hiding in the photons, no electron encoded in some recoverable local form, no way to reach into the universe's current state and pull out an electron that matches the one from Chapter 1. What is there is something more abstract and in its own way more permanent. The information, the complete specification of what the electron was, is present as a global constraint on the state of everything. The universe evolved from a state that contained that electron, and unitary evolution preserves the distinction between every state it ever passed through. The current state of the universe is one from which, in principle, with complete knowledge of everything, you could trace backward and find the electron state. In practice, impossible. In principle, required. The electron left behind a universe that remembers it. Not in any human sense, not as a record kept somewhere, a file in a cabinet, an entry in a ledger. In the physical sense, the sense where memory means a constraint on the present imposed by the past, a thread in the structure of what is that leads, unbroken, back to what was. The place where the electron was is empty. The universe is not. The question has been there the whole time. Not the technical version, not the question about unitarity or entropy curves or entanglement wedges, or the information content of Hawking radiation. Those are the scaffolding, and good scaffolding, built carefully over many chapters to hold something up. But the thing the scaffolding was holding up is older and quieter, and does not require the technical vocabulary to be felt. Does the universe remember? Not in the way a brain remembers, not as retrieval, not as narrative, not as the experience of a past moment arriving back into consciousness, with its edges softened by time. Memory in that sense is a biological process, particular to systems that evolve to use the past as a guide to the future, and the universe is not that kind of system. The universe does not have a use for its history in the way a creature navigating a landscape does. But there is another kind of memory, a physical kind, the kind that means the present state of a system carries, encoded in its structure, the complete record of every state that preceded it. The kind that means, given enough information about now, you could in principle reconstruct then. The kind that means nothing that has ever happened has been, and I keep turning this word over, looking for a better one, erased. Not forgotten, in the sense of being unrecoverable to a sufficiently complete and patient examination of what exists now. This is what the physics, taken seriously, implies. The electron we followed through this video, say, the one that approached its opposite and entered a brief bound state and then annihilated into 2 photons and sent those photons moving apart at the speed of light, carrying everything it was encoded in their entanglement. That electron is gone. There is no electron there. There will not be one again, not that electron, not the specific configuration of field excitation that constituted this particular particle with this particular history. Gone in every sense that matters to ordinary experience. And yet the information that specified it, the complete quantum description, the spin orientation, and momentum state and entanglement relationships that made this electron what it was, is present in the current state of the universe, not stored somewhere, not filed, present as a constraint, as a thread in the structure of what exists now that leads back, unbroken by any physical process, to what existed then. Thank you to everyone already contributing on Patreon. It means more than I can properly say. If you enjoyed this video and would like to help the Sleepy Physicist grow, the link is in the description. The universe does not keep records the way we keep records. We keep records because we forget. We write things down because the present does not automatically contain the past in any accessible form, because our brains are lossy and selective and the information we do not capture disappears from our reach. The physical world does not have this problem. The physical world does not forget because the mathematics of its evolution does not include a forgetting operation. Unitary evolution is the absence of forgetting, built into the structure of the equations rather than achieved by any deliberate act of preservation. What would it mean if this is true? Not just for particles and photons and black holes, for everything that has ever ended. The star that collapsed 3 billion years ago, compressing its outer layers into a shockwave that dispersed elements across a region of spacing, exists now as a constraint on the quantum state of everything those elements have since become. The galaxy that merged with another galaxy over hundreds of millions of years, each star's trajectory folded into the new distribution, is present in the current positions and velocities and quantum states of the stars that resulted. The first particle that ever interacted with another particle in whatever the early universe was doing in its first moments left a thread in the structure of what followed that has never been cut, only extended, only woven into more and more of what came after. Every vanishing is a redistribution. Every ending is a transformation of what was into the constraints on what is. Nothing leaves. Nothing, in the physical sense, is permitted to leave. The no-deleting theorem is not just a result about quantum information technology. It is a statement about the character of the universe. It does not delete. It cannot. The mathematics does not include that function. I find this, and I want to be honest that I'm not sure whether what I feel here is wonder or something closer to unease. I find this a strange thing to sit with at the end of a long video. The comfortable version of physics is a physics of things, particles that exist, fields that carry them, forces that push and pull. A reasonably clear story about what is present and what is absent, and what the difference between those two states means. The version we have arrived at is less comfortable, or maybe more comfortable in a different way, or maybe just stranger than either of those words captures. In this version, the universe is not a collection of things with gaps between them where nothing is. It is a single, continuous, unbroken record. Not a record anyone is keeping, not a record that can be read by any entity we can imagine, but a record in the structural sense. The sense where the present is the past written in a different form. Everything that has ever happened is, in some precise physical meaning of the word, still happening in the only way physics says things continue to happen, as a constraint on what can come next, as a before that is encoded in the after, as a state that unitary evolution has transformed but not erased. The electron is not there. The electron was there, and the universe, in the only sense the physics supports, has not moved on from that in the way we move on from things. It has incorporated it. The electron is in the structure of what followed. The way a word spoken into a room is in the air by pressure and wall reflections and temperature gradients for as long as those persist, which in the universe's case is, the mathematics does not give it an expiration. Does the universe remember? The answer the physics leans toward is something like, the universe does not remember, because remembering implies a process of retrieval from a separate storage, and the universe is not doing that. What it is doing is something without a clean human name. It is being the consequence of everything that happened inside it completely, without loss, without abbreviation, without the softening that time brings to human memory. The electron vanished. The place where it was is empty. The emptiness is not empty. It never was.